Good afternoon, everybody. My name is Zhang from TU Delft, the Netherlands. This is joint work with Nanyang Technological University in Singapore. So in this presentation, I will introduce our work on incorporating hierarchically organized features into recommendation. Imagine you have a set of users for whom you know where they come from. For example, their continent, the countries, the cities. With this kind of information, we may better explain user preferences and eventually better model user-IT interactions. Now, let me directly give the objective of our research. Now, we aim at developing a method that can fully exploit feature hierarchies for recommendation by using the structured information and historical data. So I will come back to this later. Let me stress the universality of feature hierarchy. Actually, feature hierarchies are a very important class of structures that can be used to organize and describe human knowledge. So they are highly important for a lot of disciplines, for instance, for biology, for chemistry, and more recently for machine learning, like the structured prediction, and also for natural language processing. But how about recommend assistance? There are actually plenty of applications, recommendation applications, where the feature hierarchies exist. For example, we can have the feature hierarchy of product category in Amazon Web Store. We may have the article topic organized as a hierarchy in Wikipedia. We can also have the music genre hierarchy like in Yahoo Music, and also like the venue category in Foursquare. So despite all of this, the research on fully exploiting feature hierarchies remains an open question. So this research, we want to tackle how can feature hierarchies be used. Okay, let me first use an example. In this slide, you can see an image where we want to describe a point of interest recommendation scenario. We have the users' items, and for the users, we have hierarchically organized feature, like the country and cities they come from. Now, the first thing we discover is that the structure of the features are very important. For example, in this example, you can see that both Alice and Bob, they like pizza very much. And this can be very much explained by the fact that they are all Italians. So, and on the other hand, the degree of the preference to pizza are different, actually. And this, to some extent, can be explained by the fact that though they are all Italians, they are from different cities of Italy. Now, this means that both the cities and the countries and the linkage between them are very important. While the state-of-the-art method usually do this by reducing hierarchies to simpler structures, like to flat structures, which can bring a severe information loss. Now, on the other hand, we can see that data is very important. For example, the different degrees of users' preference to a point of interest can only be seen from the data. So if we view this kind of influence, so if we view the characterization of users' preference by the features, we view them as influence, and such influence can only be learned from historical user-item interaction data. So that's why we said in the beginning that in order to fully exploit feature hierarchy, we need to consider both the structure of the hierarchy and also the historical data. And for this objective, our solution is recursive regularization, which is a method that is specifically designed to incorporate feature hierarchy for recommendation. Now, this is based on the latent factor model, and I guess you are all familiar with this. So the main functionality of recursive regularization is to model the feature influences Now I will introduce this step by step. Now consider a isolated feature in a hierarchy. We model the influence of an isolated feature, meaning that we only look at this feature without considering the connections to other features. Then such influence, we model it by the dissimilarity of users. If we consider the user feature hierarchy, we model it as a dissimilarity of user latent factors only for these users that are characterized by the feature. Now, for instance, the influence of feature F4 is defined as the similarity of latent factors of all users characterized by it, namely U1, U2, and U3. Now we continue to a feature unit, which is a combination of a parent feature and the children feature. And it is defined as the weighted sum of the influence of the parent feature and the children features. And we use two parameters, G and S, to weight the influence of the parent feature and the children feature. Now, for instance, in the example of feature unit F5, it is defined like this. Then we have the ultimate recursive regularization, which is defined recursively to distribute the influence of features from the root feature to the leaf features. Now, I will use an example to illustrate this. Now consider the feature hierarchy on the left top. The influence of this feature is defined like this. First of all, we have the influence of the feature hierarchy equal to the root feature. Then the root feature F5 is defined like this, as we saw before. Now, it is defined as the influence of F5 itself and also the influence of its children features. The children features can be recursively defined like this. For instance, for F5, we have this definition. And for F3, we have the influence like this. Now, since F3 is a leaf feature, we define directly as the dissimilarity of users characterized by it. Now, with recursive regularization, we can express the influence of features on users as a parameterized function of G and S. For example, if we consider U1 and U3, since both of them are influenced by features F4 and F5, then we have the influence of the dissimilarity between them like this. Now, by incorporating this regularization term into a latent fact model, we have the recursive regularization matrix factorization framework. Now, we here use a very simple parameter alpha to control the importance of recursive regularization. And the good thing of ReMF is that it can automatically learn the feature influence from historical data. As you can see that we can jointly learn the user and item latent factors and also the G and S. In other words, we can use G and S to characterize the influence of each feature on user-item interactions. Now, as a remark here, this proposed framework can work with feature hierarchies of both users and items. So before we use users as an example, and however it can also be used for items. And it can work with imbalanced feature hierarchies and scalable to a large data set. You can refer to our paper to find the detailed analysis of the complexity of this algorithm. Now we go to the validation part. In order to validate the proposed method, we collect a data set as the users Foursquare checking from two platforms, Twitter and Instagram, from 4 major European cities, Amsterdam, Rome, Paris, and London, over 3 weeks. And we use both the rating prediction and ranking prediction metrics to evaluate the performance. We use 5-fold cross-validation, and for parameter setting, we use grid search. So for a comparative method, we first use MF without considering any auxiliary features, then collective MF and factorization machine, which are two method designed for incorporating features, but in a very generic way. And on that, furthermore, we consider TextMF, which has a very similar way of incorporating features, just like SVD features. Then on the other hand, we try improve FM by designing an hierarchical features, like we consider the passes in the hierarchy as additional features to use as input to FM. Then we call this high FM. Now, let me first give the results of ReMF by considering when alpha varies from small to large, how the performance of ReMF change. And as you can see that from these 4 figures that the performance usually first decrease, then increase when alpha varies from small to large. And moreover, the curves are more or less stable, and that's why we say that, okay, ReMF is robust to parameter setting. And when compared with other methods, here I show the results of MAE, we create 2 views of each data set, namely the entire data set and the data set considering only the users with less than 5 ratings, the cold start users. Now, as you can see that, okay, MF performs the worst, which can be expected because it considers no additional feature information. And CMF, TextMF works okay. Then surprisingly, FM works very good. This might be that, okay, it considers multiple ways of interactions between users, items, and features. And by incorporating additional hierarchical features, high FM outperform FM. And overall, we can see that ReMF performed the best. And it can it achieves even higher performance in coping with the cold start users. And when considering the ranking performance, ReMF also gives a very good result. Okay, here is the takeaway message. Recursive regularization as a parameterized regularization function can better exploit feature hierarchy for recommendation because it learns structured feature influence from data on user item interactions. Okay, thank you very much.
Okay, we have time for some questions. So while people think about their questions, quick question for you would be, you mentioned that this method scales, and I know that in the paper you mentioned that you use stochastic gradient descent and you have the computational cost computation. But can you say a few words about it? Because when looking at it, even in the paper, it's not clear how this scales to large data sets and what's your experience and when does it, do you do early stopping and does it converge after a few iterations?
Okay, so first of all, the early stopping works very well, which is gives very good boost to our method. Then about the scalability, we actually, so the data set we considered here, the Foursquare checking data set, it's not very big. That's why we consider multiple cities, multiple platforms. And on the other hand, we also try to experiment with larger data sets, for which we use the Amazon product recommendation. And for that, it's a fairly big data set. And our experience is that for ratings of 100K, data set of this size, we can reach a very good result, like within half an hour. So it's okay, yeah.
Any question in the audience?
So when you talk about feature hierarchy, there's an implicit understanding that the features are categorized as like a tree.
is there also a possibility that a feature might belong to two different parents? It's not exactly a hierarchy. Is that a possibility?
You mean features, not hierarchy, but?
So could there be a feature that could have more than one parent?
With more than one?
So it's not really a tree, it's rather a graph.
Yeah. So let me, because I had a similar question, one way to reinterpret the question, if I understood right, is maybe instead of finding a real hierarchy, your method is actually just finding feature correlation. And it doesn't really matter that they're in a really nice tree, but it could be that the features are just correlated because they always are. And what you're just finding is correlations between different features at different levels. And it's not really a nicely designed tree. Is that more or less?
My understanding is that the feature hierarchy is something which is specified by the user, right? By us.
Yes, it's
right?
Auxiliary.
So there could be, for example, in Amazon, there could be a product and it has a feature which could actually belong to two different parents in the hierarchy.
Oh, so. Yeah, you mean okay. So for features of ill-defined, we haven't really considered that, but so the assumption of our method is that the hierarchy is well defined, and even though it's imbalanced, we can cope with it. Does that answer your question?
Thanks.
Okay, thank you very much.
No more questions? Okay, so let's thank the speaker again. Thank you.
Okay, thank you very much.